the introduction, and thanks to everyone for attending my talk. I'm sorry for not being there in person, but at the moment I'm not in Torino. The title of this talk is More Fast and Energy Efficient Neural Networks, a Vertical Optimization Approach. So let's get started by first understanding why we care about neural networks. Well, in the last few years, several fields like computer vision, audio processing, and robotics have been completely changed by neural networks. And to quantitatively support my claim, let's take a look at the image classification task, that is labeling an image based on its content. Here it is shown the error rate, so lower is better, over the years for a famous image classification challenge, the ImageNet challenge. When in 2012 a neural network was introduced for the first time, it was able to reduce the error rate by 10% compared to previous methods. And then in 2015, a convolutional neural network, ResNet, was able to achieve superhuman level accuracy. But that was just the beginning of the story, because 1 year later, in 2016, an intelligent agent named AlphaGo, based on a neural network, was able to win against Lee Sedol, the world champion in the game of Go. So wow, neural networks are very cool, and how do they work? So basically, a neural network can automatically learn to accomplish a task from data, and it does so by iteratively tuning its parameters through the so-called training process. So this training process is basically driven by an objective function, a loss function, that encodes the information of the task to accomplish. And then the parameters of the networks, which are called weights after the training, can be frozen such that the network can be deployed in the wild and that can process unseen example. This process is called inference. So originally, both the inference and the training of neural networks were performed in the cloud. That is powered by near infinite research and memory and computational resources. But the need for adopting these algorithms on a wide variety of platforms has recently required to moving the inference process from the cloud to the edge, that is on lightweight embedded systems. This paradigm shift brings several advantages. First of all, it can increase the user privacy as data stays local to the device. It can also reduce the latency as no more remote requests has to be performed to a server, for example. And then it can also reduce the cost of the system because it removes the constraints of having a powerful network infrastructure. But at the same time, this kind of paradigm shift also brings a huge technical challenge. Because on one hand, we have these neural networks which are very computational intensity, and they also have huge memory requirements. And on the other hand, we have these embedded systems which are tiny devices with low computational budgets, small memories, and severe power limitations. So here we need to find a way to bridge this gap. And here comes the work that I've done during these years of PhD, where basically I tried to build smaller, faster, and more energy efficient neural networks through a vertical optimization approach. The idea is that we need to specialize all the phases of the deployment stack. So from this neural architectural design, where you tune the parameters of the network, like for example, which modules you want to use, or the number of layers, the resolution of the input, and then also to the algorithmic level, where you, for example, where you can choose the bit width the bit width that you use to represent the activation, so the intermediate results of your network, as well as the parameters of the network, or for example, where you can apply some smart optimization techniques in order to remove some part of the network because it's not that important for the accuracy. As well as a bit lower in the stack when you decide how to schedule the different operations, and then finally when you implement the operator of the network. So for example, each of these nodes, like convolution or matrix multiplication, you really need to specialize the implementation to the target device as well as to the specific neural networks. So overall, in these few years, I've worked on several techniques working at different levels of abstraction, and I propose new techniques, as well as try to build a pipeline of several techniques that work in a nice way together in order to gain those savings that are needed to deploy neural networks on embedded systems. So in this talk, I will focus just on a couple of works, but then if you're interested, I will be really happy to discuss further offline. So the first work that I would like to present is how we try to address the memory wall problem. So usually tiny embedded systems are powered by microcontroller units that are low-power devices, and they have small flash memory, so a small non-volatile memory in the 1 to 2 megabytes, and then also very small RAM, so a small volatile memory in tens or hundreds of kilobytes. And then when analyze the memory cost of a neural network, this is split among two components. We have the weights, and this depends on the weight footprint, depends on the number of parameters of the network, and then we have the activation footprint that actually depends on the memory needed to store the intermediate results of the network. Now, when you want to deploy the network on an embedded device, you need to satisfy two constraints, because the weight footprint has to be less than the flash size, as well as the activation footprint has to be less than the RAM size. So if we look at the state-of-the-art literature, there are different methods that are used to reduce the RAM activation, so the RAM occupation, so the activation footprint, or the weight footprint, so the flash occupation. But for example, they also introduce inaccuracy loss. But at the same time, there are other methods, for example, pruning, that is quite interesting because the accuracy can be, so the network produced after this pruning, it can have almost the same accuracy of the original network, but you can reduce the flash footprint, so the weight footprint, but at the same time, you don't have any reduction on the activation footprint. So the pruning basically is a technique to understand, it's a technique to remove some weights from the network, so put their value to 0, by understanding which are the weights that are less important for the final outcome, so for the accuracy of the network. And then you can exploit the presence of 0 in your weights in order to compress stuff, but also to improve the latency, because also in the computation you can make use of this information of zeros. So we say, okay, but what we can do for the activation memory footprint? We started to look at the memory profile. So here I show the memory profile, the activation memory profile versus the processing time of a network for different state-of-the-art network. And we noticed that for many of them, the peak memory consumption, which is what dictates at the end the overall footprint that you need, is actually reached when processing small parts of the network, while the activation footprint is much lower for other parts of the network. And actually, this is quite common because it's related to the design methodology of neural networks today, that they use different spatial resolution throughout the network, and they also have different connectivity structures which create this imbalance in the memory profile. And so we asked to ourselves, can we redistribute the memory peaks to alleviate the memory pressure? And this is exactly what the graph level optimization that we developed, so the data flow restructuring or the graph restructuring does. In particular, it's a way to minimize the activation memory footprint without affecting the functionality of the network. And then it's by working only at the graph level, so also only on this abstract representation of the network, it can also be task and model agnostic, and it can also be independent from the target hardware device. And it basically, it's an algorithm that identifies the part of the network with the highest memory consumption, and it provides this part of the network into smaller branches which take the same input, but actually these branches can be processed independently, one from the other, and they have a much lower memory. And at the end, in this way, you can have a lower peak memory consumption, and so also a lower RAM occupation. So if we look again at the graph restructuring in this table, we can see that the graph restructuring allows us to reduce the RAM, so the RAM occupation, so the activation footprint, without touching the waste footprint and keeping the same accuracy of the network, because it only works on this graph without modifying the functionality. And then if we compose this graph restructuring with the pruning that I mentioned before, we can basically obtain a pipeline, an optimization pipeline that can reduce the RAM occupation, the flash occupation, and at the same time it can also keep almost the same accuracy of the original network. So let's try to take a look at some numbers. And here what I show is the memory space in terms of flash versus RAM, and then in green I show the physical region, which is actually dictated by the specific memory capacity of a device that we used as a benchmark. So 512 kilobytes for the RAM and 2 megabytes for the flash. So here we show the RAM versus flash occupation for a state-of-the-art neural network for different resolution. In red 192 for the input, and in blue 160 in terms of input resolution. Then we have 3 different configurations based on the width of the network, which corresponds to the number of channels. So you can think about it as working on the capacity of the network. Then, if we apply sparsity, we can basically just reduce we can do this vertical movement because we only reduce the flash occupation of the network. Then, if we apply our graph restructuring technique, we can create this left shift in the space because we only reduce the RAM activity, the RAM occupation. But then, if we apply together sparsity and graph restructuring, then all points become feasible, and then all the configurations can be deployed on the device. And then here in the chart on the right, I also show the latency for the different configurations, and we can see that basically with sparsity we can go better than the dense network, and our graph restructuring has a certain computational overhead, which is limited to the 10% in the worst case, so it's still acceptable, I would say. But then for some configuration, only the 2 combined techniques can deploy this network on the device. At this point, we asked, so is it possible to raise the bar of the efficiency even further? So we looked again at the application, at these embedded applications, and we noticed that for many always-on applications, actually the quality of results requirements change over time. And so also the energy and latency constraints of the network, of the neural network that you want to run on the time-embedded system could change over time. Now, if we can tune this trade-off between the energy, latency, and quality of results at runtime, and we can go beyond the worst-case scenario, then it will be possible to achieve higher efficiency on average. So the idea is to enable at runtime to deploy some tunable knobs that allows the network to be to change its performance versus quality of results working point at runtime. But again, it's really important when talking about deploying neural networks on time-embedded systems to think about the physical constraint of the platform. And in particular, the tunable knob that we adopt to do this runtime scaling is a key design choice. What we did in our recent work was to propose sparsity as a knob for doing this latency versus quality of result constraint. Why sparsity? Because sparsity is amenable to compression. We can simply not store the 0 elements, and also because it works as a fine-grained knob between the latency and the accuracy. And here we really worked vertically across the entire stack because we proposed a training algorithm in order to make these multi-sparse networks actually nested one into the other, such that the most sparse ones are actually a subset of the less sparse configurations. And then we worked on the compression format, so on the way in which you represent these multi-sparse matrices in a way that basically one multi-sparse matrix can be represented as a combination of multiple sparse components. And then here we applied some classical encoding techniques in order to make this compressed format really efficient. And then we also worked on this sparse computing kernel, so on how we compute basically matrix multiplication using this compressed sparse format in order to avoid expensive recording fixes. So here, let's try to take a look at some numbers. Here it is showing the storage footprint of a nested network that can work in three sparsity configurations, 70%, 80%, and 90%. And you can see that if we compare the storage footprint with the only one single sparse network working at 70% of sparsity, then the storage footprint is almost the same. The overhead is really negligible, but still our network can work in three different configurations. And then this is really cool when you look at it in terms of trade-off that you can achieve at runtime of accuracy versus latency. And here there are all our nested sparse networks compared to other state-of-the-art solutions. And you can see that basically we were able to create a new Pareto form in this space. And all these networks can be deployed on a tiny device with 512 kilobytes of RAM and just 2 megabytes of flash. So overall, to summarize this talk, what I wanted to highlight is that the key to bring intelligence everywhere is the availability of small, fast, and energy-efficient neural networks. And my idea is that the way in which we can tackle this challenge is through specialization across the entire software and hardware stack. And as a main contribution, at least for these first years of research, is that I propose different techniques that push further the boundary of accurate neural networks that can be deployed on tiny embedded devices. And now I will be glad to reply to your questions.